Thanks for joining me. We're about to go through and do some practice problems. Now, you know we've heavily invested in this. In particular, if you look somewhere down here, you'll discover there's a pause button. That's an amazing feature of this video. You see, what you can do is once you see a problem, pause. Think about how to do it. Better yet, do the whole problem. And then, once you're ready, unpause. And even if you can only do part of it, do as much as you can. The more you can do by yourself, the better you'll get. All right, let's begin. Evaluate the integral. It's a double integral, two integral signs, so we're integrating over a two-dimensional region. Our function, y squared of 9 plus y squared cosine x. What's our region? It's a rectangle. X is going from 0 to pi over 4. Y is going from 0 to 4. All right, good. Now, right now, we don't know a lot of ways to integrate. Essentially, we just do slices, right? And so when we look at this dA, well, we really have two choices, dx dy and dy dx. Now, sometimes it doesn't matter. Sometimes it matters a little bit. It won't affect the final answer, but it can affect the way you get there. So for us, this looks pretty straightforward, so I'm not going to do anything too tricky. I'll just say, let's do dy dx. So this becomes the integral y square root 9 plus y squared over cosine of x dy dx. Again, it's a choice I made. Now, as a reminder, things pair up and you work from the outside in. So the dx pairs out with the outside bounds, dy with the inside bounds. So we're told x goes 0 to pi over 4. So the first integral, 0 pi over 4. Y goes 0 to 4. So 0 to 4. Good. Now we have our integral set up. Now this is a type of integral where you can do something kind of fun, and I'll point it out. And namely, notice that this function, you can write it in a slightly different way. So this can be written as 1 over cosine. I'll just write that as secant of x. And this y squared 9 plus y squared, making it calculus friendly, y times 9 plus y squared to the half. So notice, what do we have? Well, we have the x stuff times the y stuff. And so we can actually, in some sense, separate the function out. And what that allows us to do is it actually allows us to pull the integral into parts. So because you have this nice clean separation, and because we're integrating over a rectangular region, we can do the following. And so I'm going to do it. Namely, we can say this is actually thinking about two integrals multiplying together. So I can do the x integral, 0 to pi over 4, secant of x, and then I can do the y integral, 0 to 4 y 9 plus y squared to the 1/2. You don't have to. You'll get the same answer if you just do one layer, evaluate, do a second layer, evaluate. And you have to make sure you're in the right setting. Okay, so again, function of x times function of y. So you can separate them out, rectangular region. So let's just finish it up from here. All right, well, do we know the integral of secant? Well, yeah, that's one of our integrals we know, right? It's by our heart we know that. So that's log secant plus tangent. Okay, and then we're going to evaluate 0 to pi over 4. Now, this integral, it's not on our list, but we see that 9 plus y squared and say, ooh, that's a nice looking 9 plus y squared. So we can do things with that. In particular, this one is really geared up well for substitution. So let's think about our substitution. We said u is the inside, 9 plus y squared. And then du is 2y dy. Or we could say, hey, this is really the same as saying a half du is y dy. And, okay, so what would this become? So this integral would become the integral. The y dy would be a half du. 9 plus y squared to the half, u to the half. And what are our bounds? These are y bounds. So y equals 0 to y equals 4. When y equals 0, u equals 9. And then when y equals 4, u is 9 plus 16, 25. Okay, so let's catch up to what we're doing here. So the first integral, we've already integrated. The second integral, we did substitution. So, okay, well, let's do our evaluation. Secant of pi over 4 is square root of 2. Now, if you're not familiar, you might remember that cosine of pi over 4 is root 2 over 2, which is the same as 1 over root 2. Secant of pi over 4, you just flip that upside down, so you get root 2. So you get log of root 2, and tangent of pi over 4 is 1. Now, when you plug in 0, secant of 0 is 1, tangent of 0 is 0, so you get log of 1, which is 0. Okay, so log of root 2 plus 1, that's from your first term. Now, the second term. Okay, so we have the 1/2. We're going to add 1 to our exponent, so that's 3/2, and multiply by the reciprocal, 2/3, and evaluate 9 to 25. Okay, so the 2's cancel. We have a 3. So let's see, we have a 1/3 log root 2 plus 1 times 25 to the 3/2, subtract 9 to the 3/2. Well, we can actually clean that up a little bit. Now, how do we handle 25 to the 3/2? We don't say, oh, 25 cubed is some big number, something like 15,625? No. See, because you have to do the 3/2 power, right? So the cube makes things bigger. The half makes things smaller. Do the small before you do the big. So think of it as first square root of 25. And if you think of it that way, you say, okay, well, that's easier. Square root of 25 is 5. So this is 5 cubed. Similar, square root of 9 is 3. 3 cubed. So 5 cubed, 125. 3 cubed, 27. And if you subtract 27 from 125, you get 98. On a side note, 98 is not divisible by 3. So we end up with 98 over 3 times the log root 2 plus 1. And there we go. Yep, that's the answer. All right, so we pulled it apart. If you had done it one layer at a time, you still get the same answer. The moral is, when we're doing integration, though, it's the same type of integration, right? It's the same integration we were doing back in Calc 1, single variable. And we're not going to throw anything crazy. And so just think about, okay, how would I do this if I were a Calc 1 student? So you're integrating one variable at a time. When you integrate, treat the other variables like constants. And life is good. And I can guarantee you, we're going to get a lot more practice on this. But for now, that's a great start. Use the method of Lagrange multipliers to find 3 positive numbers whose sum is minimized and whose product is 27. All right. Now, we're after 3 numbers. We can know that because it tells us 3. And they have to be positive. All right, good. We like things which are optimistic. And we say, okay, so what do we have? Well, let's call our numbers x, y, and z. So these are the numbers that we're after. So we're trying to find 3 numbers. And this is an optimization problem. We know it's Lagrange multiplier, so it's an optimization with constraint. So we want to have the sum be minimized. So we say, okay, I have 3 numbers. How do you find the sum? So the way you find the sum of 3 numbers is you add them up. So f of x, y, z, this is the x plus y plus z. This is what we're trying to minimize. All right. Now, what's the constraint? Well, there's this other statement. The product is 27. Okay, so if the product is 27, how do we do the product of three numbers? That's x, y, z. So this is our constraint. All right, good. Now, before we start, we already kind of know what the answer will be. And here's sort of the reasoning. What we see here is that there's lots of symmetry going on, which is to say, suppose I take x and y and I swap their roles. Nothing happens to the problem. What about if I swap x and z? Nothing happens. So in other words, there's symmetry in the variables. So if you can swap two variables and nothing changes, you get symmetry. And when there's symmetry in the variables, what tends to happen is that the extreme values tend to be where they're equal. So we anticipate that x should be y should be z. Meaning, if they're all equal, then let's call them all x. X cubed should be 27. Our answer should be x equals 3. So our sum will be 3 plus 3 plus 3 is 9. So that's what we think the answer will be. It could happen that it's not, but it usually will be that. Let's find out. Let's actually do the problem the way it's told. Why? Well, because if we don't follow instructions, even if there's a smarter way to do things, we won't get the credit. And we like credit. It's one of our favorite things. Okay. Well, so how do we begin? Now, you might notice this involves three things we're looking for. And that's okay. Lagrange multipliers works just as well. So we say, all right, we need to have that gradient of f equals lambda gradient g. That's our basic underlying philosophy, that the gradients are parallel. Now you might say, well, what's g? G is the constraint. So here's your g, g of x, y, z. And this really will become three equations. So you have your f sub x is lambda g sub x, your f sub y is lambda g sub y, and your fz is lambda gz. Or, working it through, f sub x is 1. That's equal to lambda. Derivative of g with respect to x is y times z. And, sorry, that's a lambda times. Should have written down that equals. All right, f sub y is 1 equals lambda times g sub y, derivative g with respect to y, x z. And fz is 1 equals lambda, gz is xy. Well, we can solve for lambda. I tend to be of the philosophy, when in doubt, solve for lambda. And we get that lambda is, well, it's 1 over yz. It's also 1 over xz. And it's also 1 over xy. Well, suppose we look at, say, the first two equations for just a moment. Say, okay, well, if I look at these two equations here, I can cross multiply. And we get that x times z equals y times z. We know z is positive because we're told that we only want positive numbers. So I say, that tells us that x equals y. Well, that's good news. That's really useful news. But you know, that's an idea so nice, we can do it twice. So you say, okay, well, what about this set? Okay, again, we cross multiply. And that says that xy is yz. Again, we can divide out the y because we know y is positive. So that says x would equal z. Like, oh, well, isn't that lovely? Okay, great. Wait, did I do that? xy, oh, that shouldn't be yz. It should be xz, I'm sorry. So y equals z, there we go. I read off the wrong one. But okay, great. X equals y equals z. They're all equal. So Here we have another relationship. And this is always going to be what happens, is when you're solving that gradient of f equals lambda gradient of g, a new relationship will come out. And we say, okay, well, now that we know x equals y equals z, we plug that in to our constraint. So we say, well, that becomes x times x times x equals 27, or x cubed equals 27, or x equals 3. So we have one point. And if there's only one, it has to be the one. And so we come to the conclusion that at the ideal location, we have x equals y equals z equals 3. Now, let's see what we have to give as our answer. Because oftentimes they might say, what is the smallest sum? Or they might say, what are the numbers? So let's see. Use the method of Lagrange multipliers to find 3 positive numbers. All right, so the answer is that the 3 numbers that we will find are 3, 3, and 3. And we're done. Yay! Yay us! Yay us! Now you might be concerned, how do you know that we did find the numbers that has this sum minimized and product is 27? Well, the thing is, Lagrange multipliers doesn't have a built-in mechanism to test. But if you're running the process and you only get one answer, it's got to be the answer, right? So just trust. Trust the process. All right, good. Progress. Evaluate the iterated integral. So we're going to go from 1 to 2 with respect to x, 1 to 3 with respect to y, 15 over 2x plus y cubed. All right. Well, let's see what's going to happen here. Now, notice we can rewrite this. It's not written in a very calculus-friendly way, so let's write it in a calculus-friendly way. So we're going to have 1 to 2, 1 to 3, 15, 2x plus y to the negative 3 dy dx. Now, this is not one where we can pull apart into 2 integrals, because it's not function of x times function of y. The x and y are sort of mixed in together. That's all right. So what do we do? We're going to do it one layer at a time. Okay, so first layer. So as we're doing our first layer, we're integrating with respect to y. How do we treat x? Like a constant. Okay, so this is like constant plus y to the negative 3. So the integral of constant plus y to negative 3, well, you would say the following. You have your 15. You'd have your 2x plus y. Negative 3 plus 1 is negative 2. Divide by negative 2, or if you like, multiply by negative a half. And we don't need to worry about compensating for the inside because the coefficient of y here is 1. We're good to go. And then we're going to evaluate. And just to help us remind us what we're evaluating, since we integrated with respect to y, I'm going to write down y equals 1 to y equals 3. Okay, so let's update here. We have that this would be integral 1 to 2. So I'm not going to integrate yet. I want to finish the evaluation. So what do we have? We'll have 2x plus 3 to the minus 2. So we put in y equals 3. Subtract 2x plus 1 to the minus 2. Okay. All right, so we evaluated. Plugged in for y. Now we work the integral for x. Okay, so we're integrating 1 to 2. We're going to integrate. We don't need the integral sign anymore. Negative 15 over 2. Okay. And what will happen? Well, 2x plus 3 to the minus 2, that's not too bad. It would be 2x plus 3 to the minus 1. You add 1. Divide by that minus 1. Well, okay, so that's really a minus 1 in front. And then be careful here. You have to compensate for that 2. Now, the technical way you do that is you say, all right, let u equal 2x plus 3, du is 2dx, and you get a half in the end. Well, after a while, you start to say, oh, okay, if I have something linear now, ax plus b, I just integrate as though it were x, and then at the end I divide by a. So in here, divide by 2. Okay, similar thing will happen here. So we have minus, we'll have a 2x plus 1 to the minus 1. We'll divide by -1, same as multiplying by -1, and we're going to divide by 2 because of that 2. And now we're evaluating from x equals 1 to x equals 2. Okay, good, good. Now we can do a few things. We can say, well, we have negative halves in both terms. We can go ahead and pull that all the way out to the front. So we have 15 over 4. And so just, that's where that's coming from. And now we do our evaluation. So we plug in x equals 2. 2 times 2 plus 3, that's 1 over 7. And it's 1 over because of that -1. Subtract 2 times 2 plus 1 is 1 over 5. So 1/7 subtract 1/5. Now subtract, plug in 1. 2 plus 3 is, well, it's 5. Okay, so it's 1/5. And then 2 plus 1 is 1/3. All right, so we've got our 1/7 minus 1/5 minus a 5th minus a 3rd. Okay, well, let's get down to a single term. Now, if we want a common denominator, we need to have something that's divisible by 7 and by 5 and by 3. If you multiply 7 times 5 times 3, you get 105. So we can say this is 15 over 4 times, we have something over 105. Well, 1 over 7, I needed a 3 and a 5, so that's a 15. 1/5, well, that needs the 3 and the 7 to get downstairs, so I'm going to end up subtract 21. 1/5 again, subtract, so again minus 21. 1/3 minus minus, okay, that's a plus a 1/3. I need the 5 and the 7, so that makes a grand total of 35. 5 times 7. Well, 15 plus 35 is 50. Subtract 42 gives 8. So we have 15 over 4 times 8 over 105. And now we can clean up. 4 goes into 8. So that leaves us with a 2 upstairs. 15 goes into 105. 15 is 3 times 5. 105 is 3 times 5 times 7. So that leaves us with a 7 downstairs, leaving us a final answer of 2/7. And we've got our integral. All right, so just it's one of those things where you just carefully work through one layer at a time. Make sure you know what the variable is. Make sure you're evaluating the right variable. And just be patient. No big surprises. Just take your time. You'll do fine. It's all good. All good. Use the method of Lagrange multipliers to find the maximum value of the function xy plus yz subject to the constraint that x plus y plus z equals 12. Okay, so again, we've got 3 variables involved. If you remember our earlier discussion, we do have a little bit of symmetry. Namely, if you swap the role of x and z, it doesn't change the problem. So I suspect that at the end, x and z will be the same. Well, let's find out. Okay, so how do we begin? Well, we have what we're trying to optimize, and now we also have our constraint. So this is our g of x, y, z. So Lagrange multiplier problems, you first make sure you know what your function you're trying to optimize is and what your constraint is. Now that we have that, we sit down and say, okay, we have our basic formula, namely that the gradient of f is parallel to the gradient of g. So we say, well, that gives us gradient of f equals some multiple of gradient of g, and we're off to the races. So this will give us three formulas. Fx equals lambda gx, Fy equals lambda gy, Fz equals lambda gz. Now, what is f sub x? Well, it's y. That's it, right? Okay, so y equals lambda. What is g sub x? 1. All right, well, that's easy. Okay, how about what is f sub y? It's an x and a z. So x plus z. And equals lambda. What's g sub y? 1. Oh, that was easy. Okay. All right, well, what about f sub z? Well, there's only one z. And that leaves us with y again. Oh, okay. Y equals lambda gz. 1. Hey, how about that? Okay. Well, when in doubt, solve for lambda. Well, kind of already done. Okay, so what does that tell us? It actually tells us a fair amount, right? It tells us the following, namely that y is equal to x plus z. Okay, well, what can we do? Well, we can say the following. We can say, look, you have your x plus y plus z equals 12. And then we can say, hey, this is the same as y plus x plus z equals 12. But x plus z is y. So y plus y equals 12. Or y equals 6. Okay, so at our optimum, y equals 6, and we also have that x plus z equals 6. Cool. Now, how do we solve for x and z? Do we have to? Let's think about what we have. Go back to our function we're trying to optimize here. So we have f of x, y, z is equal to, notice how we can factor. That's y times x plus z. So we've discovered that at the optimum, both y and x plus z equals 6. So at the optimum points, and in fact, it's not a single point, there's infinitely many points where x plus z equals 6. This is going to be equal to 6 times 6, which is 36. Now, notice this question asks for something slightly different than the last time we did a Lagrange multiplier problem. Namely, what's the maximum value of the function? It didn't ask for the point. The reason it didn't ask for the point is because there's not one point, there's infinitely many points. There's a ton of points. So any place where y equals 6 and the x plus z added together gave 6 works. All right, so our answer is the maximum value is 36. Now we might say, well, how do you know it's a maximum, not a minimum? We only found one point, or rather I should say one sort of situation, but did we find a minimum? Well, one thing you can always try is, well, let's try something else and compare. So is there another easy solution to x plus y plus z equals 12 that we can test? Well, what if we said x and y and z are all, say, 4? Okay, that's fine. Then you'd have 4 times 4 is 16, 4 times 4 is 16, 16 plus 16, 32. That's less than 36. You could even do something like, well, let's set y equal to 12 and x and z to be 0. Then you'll get x plus y plus z equals 12, but you'll get 0 plus 0, which is 0, less than 36. So this is a large value. And so we do, in fact, believe it's a maximum. And yeah, there we go. It's kind of an unusual Lagrange multiplier problem insofar as we're not finding a point, we're finding a collection of points. But, you know, math is full of fun mysteries, right? There's lots of things that can happen, but we're ready. We know the procedure. We know the ideas. We know how to solve things. We're going to be fine. We're going to be more than fine. We're going to be great, right? Yeah. Let R be the region where x goes from 0 to 3 and y goes 0 to 3. So it's a square. 0 to 3, 0 to 3. Okay, great. That seems like a lovely region. It's the kind of region we'd like to take home to meet our family. All right, now we're asked to integrate over our region the function y sine pi 6 xy. Now, we cannot pool this into two functions, one just involving x, one just involving y. The issue is this xy on the inside. There's no way to separate it. Okay, that's fine. That means that we're going to have to do it 2 layers. But you notice something here. They gave us our region, but they didn't give us the bounds. Isn't that interesting? And the way that we integrate is we're always thinking of slicing, and I call it slice and dice, right? We're chopping it up into slices, figuring out what happens in each slice. So because they didn't tell us the order, we really have 2 choices here. We could say, dx, dy, or we could say dy, dx. So let's write both integrals down, and then we'll make a decision about which one we want to do. Sometimes it matters, sometimes it doesn't. But sometimes it matters, and sometimes it doesn't. All right, Steve, come on. So integral y sine pi 6 xy, and let's say we do the dx dy version first. So the outside layer is going with the y. Y goes 0 to 3, so that's a 0 to 3. The inside layer goes with the x, and x goes 0 to 3, so that will be 0 to 3. Okay, versus integral 0 to 3, integral, spoiler alert, I already gave it away. All right, I'll talk about where those bounds come from. Pi 6 xy dy dx. So our bounds y, outside bounds are x goes 0 to 3, inside bounds are y goes 0 to 3. Normally, these will not look the same, and they're actually not the same. And I want to point out, you might say, Steve, I have eyes. My eyes can see. These are the same, Steve, but they're not. Insofar as when we write the bounds here, this really is saying from y equals 0 to y equals 3, and x equals 0 to x equals 3. So bounds have sort of this hidden, x equals or y equals. On this side, it would be x equals to x equals, and y equals to y equals. Okay, so there is some slight difference there. Even though they may look the same, it's because we're hiding the parts where they're actually different. Now, let's talk. Real talk. Me and you. We need to have a conversation. Which integral would we prefer to do? And oftentimes I think of which one's going to be the easiest to start with. And I say, well, this integral, good news, integrating with respect to x, there's only one x. I'm treating y like a constant. No big surprises. This integral, there's 2 y's. So if we're integrating with respect to y, since we have 2 y's, what would we need to use? Integration by parts. That doesn't sound fun. That sounds like you need to know stuff. And our goal is to, we want to know stuff, but our goal is to try to be gentle and kind to ourselves. So here, if we were to start, this would involve integration by parts. And that sounds messy. So let's try the other way first. So oftentimes, a smart choice in the way that you integrate things can lead to very positive outcomes. So if we're doing it here, remember we're treating y like a constant. So we'll have integral 0 to 3, as before, because we haven't integrated. We have this y here. What's the integral of sine? Integral of sine is negative cosine. Okay, so we have a negative, and then we have a cosine of pi over 6 xy. What else do we have? Well, because this isn't just sine x, right? So if the integral of just sine would be negative cosine. Because it's not just an x, there's this extra constant floating around. And right now that constant looks like pi 6 times y. So how do you compensate for a constant on the inside? You flip it over and write it in front. So pi over 6 times y, when you flip it over, it becomes 6 over pi y. And then we're going to do an evaluation. And this is from x equals 0 to x equals 3, because we integrated with respect to x, so we're evaluating our bounds, dy. Okay, so this last part is the part that often can be a sticking point. So let's make sure we count one more time what's happened. The y is a constant, just comes along for the ride. This minus is because the integral of sine is negative cosine. And now, if I was integrating, think of it as like sine of 4x. What would you have? Well, you'd have a negative cosine 4x times the fourth, or divide by 4. Well, the 4 is the same as the pi over 6 times y. It's a constant. So the point is we're flipping that. And so if you flip pi over 6y, it's 6 over pi y. Okay. Now, what do we have? Well, let's clean it up. Notice the y's cancel, almost as if we planned it. And we did, actually. Whoever wrote this problem planned it to be nice. And so that's going to make our life a lot simpler. So what do we currently have? Well, we still have the integral because we haven't done it yet. And we have a minus 6 over pi and a cosine. And we're going to plug in. So we're plugging in x equals 3. So we have a cosine pi over 2. We're plugging in x equals 3, so that's pi over 2y. And then subtract cosine pi over 6 times 0 times y. Well, that's going to be cosine of 0. Cosine of 0, also known as 1. So minus 1. Okay, so we'll just make some notes here. This is what we get when you plug in x equals 3. This is what you get when you plug in x equals 0. All right. Nice. Nice. Okay, so we're making good progress here. So our next thing is we integrate again. So I'll pull the minus 6 over pi all the way out in front. And, oh, bad notation, Steve. Don't forget this part right here, because we've got to keep track of what we're integrating with respect to. Integrating with respect to y. So what's the integral of cosine? Integral of cosine is positive sine. So we're going to have a sine of pi halves y, but then you have to flip the pi halves over. So that becomes a 2 over pi. Okay, so that's the integral of cosine pi halves y, 2 over pi sine pi halves y. And then the integral of 1 minus y. And then we're going to evaluate from 0 to 3. Now the good news is we can see when you plug in 0, sine of 0 is 0. And 0 is 0. So we're only going to have to plug in 3. All right, so we're almost there. We have our minus 6 over pi times 2 over pi sine of 3 pi over 2, and then subtract 3. Okay, And then, as we said, this is subtract 0. So when you plug in 0, you get 0. We want to really finish up. Let's get all our trig taken care of. Think of the unit circle. And we say, okay, if I'm on the unit circle, where is 3 pi halves? That's the same as going 270 degrees. So sine of 3 pi, well, 3 pi halves is this point right here, which is at location 0, negative 1. And the sine is the y value. So sine of 3 pi halves is negative 1. So finally, we can multiply the negative 6 over pi through. Everything's negative, so that's going to get rid of all the negatives. So we're going to have a 12 over pi squared, right? 6 over 2, pi over pi. And then a plus 6 times 3 makes 18 over pi. And there we go. We're done. You made it. Woohoo! Yes. All right. Well, it's just make a good choice at the start, and life will be better. And now, if you did on integration by parts, the first step would have been hard, but the next step would have been impossible. So think about it. Think, well, what's the right way for me to integrate? And maybe, if you're getting stuck, go back and try a different route. The road not taken. That might be the way to go. Find the point ABC on the sphere x squared plus y squared plus z squared equals 56, where the function f of x, y, z equals x minus 3y minus 2z attains its maximum value. Okay, so what kind of problem are we at? We're trying to optimize, because we see we're trying to get a maximum, and there's a constraint. Constrained optimization means Lagrange multipliers. Okay, so we're doing a Lagrange multiplier problem. Okay, so we'll start out, and I'm going to write underneath here just for reference, g of x, y, z equals x squared plus y squared plus z squared equals 56. So we start all Lagrange multiplier problems once we've clearly identified our two functions f and g by saying we need the gradient of f to be parallel to, or a multiple of, the gradient of g. All right, so that in this case is going to become three equations, namely f sub x is lambda g sub x. Well, f sub x is 1. That's going to equal lambda g sub x is 2x. And fy equals lambda gy. Okay. Well, f sub y is negative 3. That equals lambda g sub y is 2y. And our last is fz is lambda gz. Okay, well that's negative 2 equals lambda, and then derivative of gz is 2z. All right, good. Now, what do we do? Well, we have three equations, and this is one of those times we would say, let's solve. We know none of x, y, and z are 0. We know lambda is not 0. And you might say, how do we know that? Well, because if any of x or y or z were 0, we'd have 0 times something equals a non-zero number. Same thing for lambda. So I'm going to solve for lambda. It's my favorite technique. So we get that lambda, that's 1 over 2x from our first equation, but it's also equal to minus 3 over 2y, that's our second equation, but it's also equal to minus 1 over z. That's our third equation. The twos end up canceling. Okay, well, let's look and see, hey, what is this telling us? Well, we can, for instance, take the first two equations and say, well, that tells us something. Cross multiply to get rid of our fractions. And we get that 2y is equal to minus 6x, or if you like, y is negative 3x. All right, well, good. Progress, right? Now, what if we take the first and the third equation and we compared those two? Right, because we can do that. Well, if we did that, we'd have the 1 over 2x is equal to minus 1 over z. And if you cross multiplied here, you'd end up with z equals minus 2x. Like, oh, okay, all right. Sure, we can say that. And so now we have extra relationships. So y equals minus 3x, z is minus 2x. And that gives us information. So we're going to use those new relationships that came from gradient of f equals lambda gradient of g and put them into our initial constraint. And the moral of Lagrange multipliers is to say, oh, we're trying to take this relationship, gradient of f equals lambda gradient g, and find more things about how x, y, and z relate to help us use our constraint to figure out what x, y, and z are. So we have the following. We have our constraint x squared plus y squared plus z squared equals 56. Well, that becomes x squared plus negative 3x squared plus negative 2x squared equals 56. Okay, all right. That would be x squared plus 9x squared plus 4x squared equals 256. And here you add those together. That's 14x squared equals 56. And divide by 14. Turns out 56 is divisible by 14. Almost as if someone had planned it. Because they did. And we get that x squared equals 4. That leads us to x equals plus minus 2. All right. Good. Now, this is going to lead us to two possible points, right? So we have the x equals 2, and we have the x equals minus 2. So suppose x equals 2. In that case, y would be negative 6, which is negative 3 times 2, and z would be negative 4, which is negative 2 times 2. If x equals negative 2, y would be positive 6, and z would be a positive 4. So we have two candidate points. And, well, we'll test both of them. So when we plug in 2, negative 6, and negative 4, what do we get? Well, we get 2. Negative 3 times negative 6 is plus 18. And negative 2 times negative 4 is plus 8, which would give us 28. On the other hand, if you plugged in negative 2, positive 6, positive 4, you'd have negative 2, and then minus 18, 3 times 6, and minus 8, 2 times 4, and that would be a negative 28. Now, these are the only 2 points coming out. And we can actually say definitively it's one of these 2 points. The reason we can say that is our region is a sphere. So we have a sphere, which means we've got something which is closed and bounded. So we know we attain an absolute max or an absolute min. Lagrange multipliers will always find it if you have something which is closed and bounded constraint. So we now look at this and say, which one's bigger? Well, good news, not too hard to figure out. 28's the bigger value. Now, are we looking for the value or the point? And we see it says find the point where the function attains its maximum value. So it's just after a point. So our answer will be 2, negative 6, negative 4, and that's it. We found it again. Huzzah, huzzah, huzzah. Now, I just want to make some comment here. I noticed on this quiz, there's been lots of problems with Lagrange multipliers involving 3 things, x, y, and z. That's great, but don't forget, a lot of problems involving Lagrange multiplier involve 2, just x and y. So don't anticipate that everything involves an x, y, z. Also make sure you get some practice with problems involving just x and y from somewhere. All right? Good. Practice, right? Practice makes you a little bit better. All right. Find the absolute maximum value of the function f of xy, x squared minus 8x plus y cubed, on the closed triangle bounded by the lines x equals 0, y equals 5, and y equals x over 2. All right, so let's sketch what our region looks like. So we're in, I should draw my axes first. So we have x equals 0, also known as the y-axis. We have y equals 5, okay. And then we have this y equals x over 2. So it's a shallow line running up. So y equals 1/2 x. And all right, good. And so yeah, this bounds a triangle. And we want to have the closed triangle bounded by the lines. So the implication here is we are also considering points on the inside. Okay, so there we go. Now, this is our make a list. So we're going to make a list. And if we're going to make a list, we've got to know a couple of things. Let's talk about our corners. One corner is pretty easy, the origin. This corner is also pretty easy because we know that x needs to be 0 and y needs to be 5. And now this one maybe not quite so easy, but we know y is 5, so that's good. That gives us our second coordinate. And on the other hand, if I think about it, this says x is 2y. So since y is 5, that says the x coordinate is 10. All right, good. Now, we can begin. And, okay, so we're going to make a list. We're making a list. We're checking it twice. Well, we're still making the list phase. I always like to throw my corners in near the start. Just, it helps me feel like I've done something. Progress, right? Yeah, progress is important. Okay, so we'll start by doing a check for internal points. So for the internal points, what do? Well, we set the gradient of f equal to 0, or really we say f sub x, which is 2x minus 8. Set that equal to 0. That gives us x equals 4. And f sub y, which is 3y squared, we set that to 0. We get y equals 0. So we end up with the point 4, 0, which is over here. Do we care about that point? Not for this problem. That point is outside the triangle. Okay, well, great. So we don't need to worry about this. So there's no internal points. Okay, well, that leaves us with 3 boundaries. So let's work through our boundaries. We've got our left side. So left side, namely x equals 0. So then our function becomes f(0y). So that becomes 0y cubed. We can take a derivative of that. We get 3y squared. Set derivative equal to 0. And that gives us that y equals 0, which would be this point down here, 0, 0. It's already on our list. Okay, well, that's saved us some work. All right. How about the top side? That's y equals 5. Well, all right, we can work that out. So we have f of x comma 5, and that would give us x squared minus 8x plus 125. We can take the derivative. We get 2x subtract 8, and set that equal to 0. That gives us x equals 4. Or, if you like, that's the point 4, 5. And that would be here. So that is a potential place. So we add it to our list. 4, 5. All right. And then there's the side which is, at an angle here. Let's call it the sloped side. Okay, so this is y equals a half x. All right, so what do we have here? Well, we really have f of x comma a half x. So this becomes our x squared minus 8x plus 1/2 x cubed. It was 1/8 x cubed. And take our derivative. We'll get 2x minus 8 plus 3/8 x squared. Ugh. Okay. And, well, if you set that equal to 0, then we're going to end up with some numbers here. Let's multiply through by 8 and rearrange. So this is really 3x squared plus 16x minus 64 equals 0. And, well, when in doubt, we are going to just figure out where the x coordinate is. And, all right, so that would be x equals negative 16 plus or minus the square root 16 squared minus 4 times 3 times 64 all over 2a 6. Well, this is looking not very good. So there's a negative 64, so that makes this a plus. And okay, so we end up with some big numbers here. So negative 16 plus or minus. And here we have 256 and 12 times 64. That's 10 times 64, 640, and plus 128. Okay, so that would add up a 4, carry the 1, 6, 10, 12, carry the 1, and let's see, that'd be 7, 9, 10, 1,024. So that's 1,024. Now, what can we say about the square root of 1,024? Well, it turns out 1,024, that's 2 to the power of 10, because we're all powers of 10. We love our powers of 10. So, square root of 1,024 is 2 to the power of 5, also known as 32. Now, if you take negative 16, subtract 32, that'll give you negative 48. Over 6 is negative 8. That's way out. Forget it. But if you take negative 16 plus 32, okay, so you get negative 8, forget it. Negative 16 plus 32 is positive 16, divide by 6, which would give you 8 divided by 3. And 8/3 is actually okay, right? Because that's an x value. It's a little less than 3. It's like if you're writing this as an engineer, you'd say, oh, this is 2.6666. So that would be somewhere roughly here. Okay, so that's our x value. Remember, y is half that. So our other point is 8/3, 4/3. Okay. Whew. All right. Well, that was a workout. But we've got our left, top, and sloped sides figured out. And we've got 5 points to test. And we'll plug them all in. Okay, so we plug this into our function. Now, the good news is some of these are pretty easy to plug in. And, well, plug in 0, 0, 0, 0, 0. Great. How about 0, 5? 0, 0, 5 cubed, 125. How about 10? 100 minus 80 is 20. 5 cubed is still 125. 145. Okay, how about 4 comma 5? Well, you're going to get 16. Subtract 32 is negative 16 plus 125. So 125 subtract 16 is 109. What about 8/3, 4/3? Okay, well, you're going to end up with, well, 64 over 9 minus 64 over 3 plus 4 cubed. That's 64 over 27. And, well, okay, let's just estimate it. The real question is it anywhere close to that? And the answer is no. Right? 64 over 27, that's smaller than 3. 64 over 9, well, that's smaller than 7. And 64 over 3, that's about 20. This is a fairly negative number, and so we can say, look, this is less than 0, but we're after the max, and we just need enough to know if it can be a candidate. So I don't need to know the exact value, I just need to know enough to rule it out. Okay, so that's ruled out. So now we look at these numbers. I have a negative number, then I have a bunch of numbers that are pretty big and a 0, and I say, well, what's the biggest one? The biggest one is in this corner, 10, 5. So our absolute max is this number 145. Done. Now, realistically, this is not how we'd solve this. There's actually a much easier way to see the answer. So I want to point out that there are simpler tools. Look at this expression. If we did completing the square here, we'd say, well, f of x, y, I can think of this as x squared minus 8x plus 16 minus 16. So that would make this x minus 4 squared plus y cubed minus 16. So this is just another way to write the function. Now, think about what this says. I'm trying to make this big. And I say, okay, well, the goal, if I want y cubed to be big, I say, well, let's make y big. Okay, so I should probably move up. Now, this x minus 4, what's true? I want x to be far away from 4. So make x far from 4. Because the farther you are from 4, the bigger you are. So that says you want to be moving away from 4. Now it turns out that if you say, I want to make y big and make x far from 4, there's one that does both of them at the same time. So our max had to have occurred at the point 10, 5. So even if we didn't know anything else, we'd be like, oh, our max has to be occurring over there. Because that makes y big, that makes x far from 4. And no other point does that. There's no trade-off. See, optimization, sorry, I'm going to wax philosophical for a second here. Optimization is ultimately, at the end of the day, about trade-offs. It's like, well, I could make this bigger, but it comes at a cost. And the question is, where's the sweet spot where the trade-offs work out just right? This one, there's no trade-offs to make. You know, run to the corner, and that's where the max will be. All right, anyways, just a comment here. You're probably like, oh, can I write this as the answer? No, do the work. Do the work. But know in the back of your head, hey, in the future, be open to thinking about problems. It's sometimes it helps to step back and say, whoa, what am I trying to do? What's really going on? And oftentimes, that'll make life a lot simpler. Find the absolute maximum value of f of xy equals x squared minus y squared on the closed and bounded set, our region, x squared plus 3xy plus 4y squared is less than or equal to 28. Now, it's not entirely clear what this set is, but essentially it's an ellipse. It's an ellipse that's been tilted slightly. And so it's not going to be the easiest thing to draw, but let's just say I'm going to assume it's true. All right. Now, we see it's an absolute max problem because it says absolute max. So we're like, oh, we're making a list. That's right. So we're putting in our sort of list mindset. Okay, so if we're going to be making a list, we say, well, let's look for where could our max happen. Well, one place it could happen is in the interior. So I say, okay, let's just quickly check there. Usually interior is not too bad to check. It's the same as saying the gradient of the function we're trying to optimize is 0. And all right, so that says f sub x, which is 2x equals 0, and f sub y, which is minus 2y equals 0. Well, that gives us two equations and two unknowns. But it's a nice kind of two equations, two unknowns. Insofar as like, we can solve this. And we can solve it quickly. X has to be 0, y has to be 0. That leads us to a single point that's on the interior. And it is true that 0, 0 does work, right? Because if you take 0 plus 0 plus 0, it is less than or equal to 28. So 0, 0 is on our list. Okay, good. Whew. Now, the boundary. And here things are getting interesting. Because our boundary is what? Where our boundary would be if instead of less than or equal to, we had equals here. And that's not a straight line. It's, well, we've already said what it is. It's this ellipse, but, you know, it's been tilted. Okay, so how do we handle that? Well, if you think about what we have on our boundary, you say, well, you know, what you're really doing is you're trying to optimize our function f of xy equals x squared minus y squared, given that we have our condition satisfied. So I'll call this g of xy, which is x squared plus 3xy plus 4y squared equals 28. Now, it's like, oh, it's like we're trying to optimize a function with a constraint. And that's because we're trying to optimize a function with a constraint. It's what we're doing. It's literally what we're doing. Okay, well, that helps us a lot. It says, oh, so we can do Lagrange multipliers for boundary. So if you have any kind of boundary curve, which is a little bit of like a strange function, or anything like implicit, for example, then you say, well, look, instead of solving, I don't have to solve, I'll do Lagrange, and I'll carry it out. Okay, so now we've got our plan, Lagrange multipliers. So we say, okay, so on the boundary, we're going to look for where does the gradient of f equal lambda gradient of g? Well, that's going to lead us to some equations. So gradient of f, 2x, equals lambda gradient of g. That would be 2x plus 3y. Now, I should say f sub x equals lambda g sub x. F sub y minus 2y equals lambda g sub y. So that would be 3x plus 3x plus 8y. There we go. So I'll write down what we just did. Fx equals lambda gx, Fy equals lambda gy. Okay, so what do we do? Well, it's not so clear, right? And so when it's not so obvious, you say, when in doubt, solve for lambda. So, because why? We're trying to get a relationship between x and y. That's our ultimate goal. So we're trying to extract a relationship about x and y from this set of equations. And in particular, we're trying to remove lambda. Well, the easiest way to remove lambda is to solve for lambda, and then, okay, what does that force? Now, for us, it says, look, lambda from the first equation, that's our 2x over 2x plus 3y. And from the second equation, that's minus 2y over 3x plus 8y. All right, well, that's, okay, that's fine. Now, cross multiply. All right, so we'll do some cross multiplying here. And that leads us to the equation 2x times 3x plus 8y. is going to be equal to minus 2y times 2x plus 3y. All right, 6x squared plus 16. Actually, before I do this, let me just cancel the 2's, because both sides have a 2. So that gives us 3x squared plus 8xy minus 2xy, equals minus 2xy minus 3y squared. Or all on one side, 3x squared plus 10xy plus 3y squared equals 0. All right, now, if we've lived a good, clean algebra life, this should factor. And looking at it right now, it's sort of like, maybe we haven't lived such a good, clean algebra life, Steve. This is not looking the best. But let's have faith. Okay, suppose we think it's going to factor. What would be true? Well, notice that nothing has a common factor. So that says I can't have repeated factors in my individual terms. And the other thing is I see 3's. So, okay, so that says the only way to break 3 up is as 3 and 1. I can't put the 3 here for 3y, so it has to be going there. And everything's positive, so let's try that. And does it work? 3x squared, yep. 9xy plus xy is 10xy and 3y squared. Good. So that leads us to 2 possibilities. Okay, so what are our 2 possibilities? And we'll mark them here. We have 3x plus y equals 0. And, okay, let's start with that one. So that says y equals minus 3x. Now, we're going to take this relationship and go back to our constraint. So everywhere where we currently see a y, we're going to put a minus 3x. So we have an x squared plus 3x times minus 3x plus 4 times minus 3x quantity squared equals 28. Now, that's x squared. So 1x squared minus 9x squared. Then you have negative 3 squared is 9 times 4 is 36. X squared equals 28. Well, what happens if you take 1 minus 9 and add 36? You get 28. Right? I think so. Let's double check. Now I'm nervous. I don't know why I'm nervous. But 1 subtract 9 is negative 8. Negative 8 plus 36 is 28. Yeah, all right. Well, that worked out surprisingly well. So, huzzah, x squared equals 1. So that tells us x equals plus or minus 1. Now, if x equals 1, y equals negative 3x, so that gives us 1, negative 3. And if x equals negative 1, y equals minus 3x, which gives you a positive 3. So those are on our list. So let's add them. 1 comma negative 3, negative 1 comma positive 3. Okay, well, next we have to go and do the other option, right? So if x plus 3y equals 0, what does that tell us? Well, that tells us that x equals negative 3y. So we're going to plug that back into our constraint. So we have x squared, well, that becomes negative 3y squared plus 3 times x, which is negative 3x, times, negative 3y times y. I can copy this right down. So x becomes negative 3y, and then plus 4y squared equals 28. So what do we have? Well, this becomes negative 3 squared is 9. 3 times negative 3 is is minus 9 and plus 4 times y squared equals 28. Well, 9 minus 9 cancels. Divide, you get y squared is 28 divided by 4, which is 7. Well, that's not the most convenient number, but it's not the most inconvenient number. I've seen worse, because we can solve if y squared equals 7, y equals plus or minus the square root of 7. Okay, so if y is plus the square root of 7, what's x? Minus 3 times that. So minus 3 root 7. And if y is minus root 7, so minus root 7, what's x? Minus 3 times minus root 7, which would be positive 3 root 7. So those are 2 points coming. And this other possible constraint. So we have minus 3 root 7, comma root 7, and then we have positive 3 root 7, negative root 7. And now we've done the boundary. So we use the method of Lagrange multipliers to add 4 points from the boundary. There's no corners because it's built into the system for Lagrange multipliers. Okay, we've made a list, and now plug it in. All right, so we're nearing the home stretch. And all right, so we plug in all of these into our function. Well, 0 minus 0, that's easy to compute, that's 0. Okay, how about 1 minus negative 3 squared? Well, so that's 1 minus 9, that's negative 8. And here, because we're squaring, it's still 1 minus 9, negative 8. How about here? Well, the good thing is we're squaring. So if we take this, it becomes 9 times 7 is 63, subtract 7. So 63 subtract 7 is also known as 56. Okay, same thing, right? 3 squared, square root of 7 squared, 9 times 7, 63. Subtract 7, 63 subtract 7, 56. And, all right, so we have possible values are 0, negative 8, and 56. Well, we're looking for the absolute max. The largest values are the positive 56. So the absolute max is 56. And that's it. We're done. See? It's not so bad. We fit it on one page. How bad could it be? Well, there are steps, right? You have to know the steps. That's why you practice. And so once you practice, it becomes very automatic. So keep practicing till it really, you say, look, I can follow the flow of the pattern. I know how this problem will go. And then just be patient. Don't rush things. It's easy to make small mistakes. So take your time, especially when you're saying, okay, well, what does that tell us about our constraint? And you can do this. You can do this. For the following function, give the absolute maximum value and the absolute minimum value and the points where the values occur on and inside the square with the vertices 0, 0, 3, 0, 3, 3, and 0, 3. Okay, so we've got a workout ahead for us because we have a square. And squares, it turns out, have 4 sides. True story, true story. All squares have 4 sides. So let's draw our region. And it's a square where we've got a corner at 0, 0. Then we go out to 3. We go out to 3. We have another corner here at 3, 3. And so now it's on our inside. Okay, so that says we've got this nice region here. And all right. Good. So we're going to be making a list. And it will probably be a long list. So when we start making our list, what do we start looking for? Well, we start looking for interior and boundary. So let's start with the interior. So for the interior, we've got gradient of f equals 0. So that says f sub x, which is 2x minus 2 equals 0. F sub y, which is 6y minus 6 equals 0. And we say, oh, well, hey, wouldn't you know that? That leads us to x equals 1 and y equals 1. That's the point 1, 1. That would be roughly here. That's a point in the square. Makes the list. All right, so let's make our list over here. All right, so list is, 1, 1. Okay, now that's the interior. Let's move and start talking about the boundary. So for the boundary, you always should include any corners. So you've got your 0, 0, 3, 0, 0, 3, 3, 3. And then you have to test each individual side. All right, well, what'll that be? Well, we've got 4 sides. We should label them. We have a side over on the left where x equals 0, side on the bottom where y equals 0. On the right is x equals 3, and the top is y equals 3. So we're going to do this 4 times. So we'll start with the left. And this is x equals 0. We have f of 0 comma y equals 3y squared minus 6y. We take a derivative, 6y minus 6 equals 0, and that says y equals 1. So that would be this point right here. That is the point 0 comma 1. Okay, well, now let's do the bottom. That would be y equals 0. Okay, so that's f of x comma 0. And that would be x squared minus 2x. Take a derivative, 2x minus 2 equals 0, and that leads to x equals 1. And so that would be right there. Okay, that makes the list. Okay, how about the right side? That's the side x equals 3. Well, so that's f of 3 comma y. That's 9 minus 6. Right, 3 squared minus 2 times 3. That's 3 plus 3y squared minus 6y. Take a derivative, 6y minus 6 equals 0. Y equals 1. That's right there. So that gives the point 3 comma 1. What about the top? Yep, got to include that. That's y equals 3. So that's f of x comma 3. Okay, so if you plug in y equals 3, you get 3 times 9, 27. Subtract 18 would be 9 plus x squared minus 2x. Take a derivative, 2x minus 2 equals 0, x equals 1. So that gives you this point here, which is the point at x equals 1, y equals 3. And that's our list. Okay, well, not too bad, other than the fact that we now have to test every single point on this list. Before we do that, I'm going to point something out. This can actually be rewritten in a sort of a nicer way. So if we group the x's together, this is the same as x squared minus 2x. And if we group the y's together, and let's go ahead and pull out a 3, y squared minus 2y. And, well, okay, x squared minus 2x, that's almost a perfect square. If we add 1 and subtract 1, similar, y squared minus 2y, add 1, subtract 1. And lo and behold, what do we get? We get x minus 1 squared. Here, we'll get plus 3, y minus 1 squared. And then we have here, notice this, minus 3 and a minus 1. So that makes a minus 4. Okay, and so we can plug in to either this expression or to this expression. So suppose we use this expression, f of 1 comma 1, 0, 0, minus 4. Okay, how about f of 0, 0? Well, actually, here, this is easier, 0, 0, 0, 0. So f of 0, 0 is 0. All right, f of 3 comma 0. Well, that would be 3 minus 1 squared, that's 2 squared, 4. 0 minus 1 squared is 1 squared. So we get 4 plus 3 minus 4, so we end up with 3. F of 0 comma 3, 1 plus 3 times 4, so that's 1 plus 12, 13, subtract 4 is 9. 3 comma 3, 2 squared is 4, 2 squared is 4, so you get 4 plus 12, 16, subtract 4 is 12. All right, 0 comma 1. Well, that's going to go away. You get 1 squared, subtract 4, and you'll end up with negative 3. 1 comma 0. That goes away. 1 squared is 3. 3 minus 4 is negative 1. 3 comma 1. You'll have 2 squared, which is 4. That goes away. 4 minus 4 is 0. So that's 0. 1 comma 3. You'll get 1 minus 1, 0. So that goes away, 0. And then you have 3 times 4, 12, minus 4 is 8. Okay, so those are the numbers. Now, we take a look and say, which one's the biggest number? The answer? 12. 12's the largest. Which one's the smallest number? Negative 4. That's the smallest. So, and notice there's no repeats for the largest or smallest. So the absolute max is 12 at the point 3 comma 3. Absolute min is negative 4, and that's at the point 1 comma 1. And there we go. We got our answer. So these problems can take a while. No individual part is hard. It's just there's lots of parts. And whenever there's lots of parts, there's always a chance of making small mistakes. So just be patient, take your time, and just be methodical. Have a plan. Don't just randomly jump around. Have a plan. So I like to say, let me start with the interior, let me add the corners, let me work through every one of the bounding edges, and then work through plugging it in. And it works. I think it works really well. I hope you find something that works well for you. All right, good. That's almost there, right? Almost there. Find the absolute or global maximum and minimum values of the function y squared plus 2x squared minus 2y minus 4x in the closed triangular region bounded by the lines x equals 0, y equals 0, and x plus y equals 3. And it says in quadrant 1. Okay, so let's just sketch what's going on. So we have x equals 0, also known as the y-axis. So we have this line here, x equals 0. We have y equals 0, also known as the x-axis. And x plus y equals 3. One way you can write that is y equals 3 minus x. So it has intercept up here at 3, slope of minus 1, So if you come down here, it also intercepts at 3. Now it extends, but we only really care about the first quadrant. And so we say, okay, so we have this closed triangular region bounded by the lines. So we want to be in the triangle. All right, so here's our region. Okay, so now what do we do? Well, we're just going to work the process, right? We've done a few of these already if you've been working through them methodically, so there's not going to be a lot of surprises. We haven't the problem where we're looking for an absolute max and absolute min. We've got a closed bounded region, so there has to be one. So what do? Well, we're going to make a list. We're going to make a list, and that list will tell us where to check. And our absolute max and absolute min will be somewhere on that list. Now, the first place to look in our list, so we're making a list over here. Here's our list. Well, we have the interior. So the interior, how do you check that? That's gradient of f equals 0. So that leads us to the equations. Take f sub x, which is 4x minus 4 equals 0. Okay, that would lead us to x equals 1. And f sub y, which is 2y minus 2 equals 0. That leads to y equals 1, or the point 1 comma 1. Okay, now is that in here? Well, it turns out yes, it's right there. So 1 comma 1 is in the triangle. So it's a point on our list. All right, now 3 sides. Let's start. You have the x equals 0 side, so we'll call that the left side. And we know how to describe it. We have a formula, namely x equals 0. So for the left, at x equals 0, we have our f of 0 comma y, so we're on here, is what? Well, it's y squared 0 minus 2y 0. Take a derivative, 2y minus 2 equals 0. That says y equals 1, but we know that x equals 0, so that gives us the point 0 comma 1. And so that would be here. Okay, that's a point on our set. So that makes our list. Okay, how about the bottom? All right. Well, that's y equals 0. Okay, so that looks like f of x comma 0. So we already see a y put a 0. We get 2x squared minus 4x. Take the derivative, because we're down to one variable. And we see that, it's x equals 1. So it's at the point 1 comma 0, which is that point. That's in our set. It makes our list. Okay, one more side, the slope side. Now this is the side which is going to take us some time. So the slope. And let's write it as y equals 3 minus x. So our function becomes f of x comma 3 minus x. Well, let's see what that gives us. So we're going to have to be patient here and work our way through it. So we have a 3 minus x squared plus 2x squared minus 2 times 3 minus x minus 4x. So everywhere we saw y, we put in 3 minus x. Now before we do anything else, let's expand this. So this becomes x squared minus 6x plus 9 plus 2x squared minus 6 plus 2x minus 4x. So here we're just expanding our terms, and now we're going to group. So we see there's an x squared and a 2x squared. That makes 3x squared. A minus 6x, a plus 2x, that makes minus 4x minus another 4x, so that makes minus 8x. and then we have a 9 and a minus 6. And so that makes up plus 3. So we've got the x squares accounted for, the x's accounted for, and the constants. Now, take a derivative, and we get 6x minus 8 equals 0. That would say, okay, x equals 8 over 6, also known as 4 over 3. Now, the good news is 4 over 3 is between 0 and 3. Or maybe I should say the bad news is it's a point we have to care about. Now, if x equals 4 over 3, remember y is 3 minus that, so y would be 9 over 3, subtract 4 over 3, which would give us 5 over 3. So we get the point 4 over 3, comma 5 over 3. That's somewhere, I think it's a little bit biased to there, I think. Roughly. It's hard to nail it down exactly. But okay. 4 over 3, 5 over 3. Now, one more point, or points, I should say, and usually I do these sooner, but make sure you don't forget what hasn't been included on our list yet. The corners. Don't forget the corners. Absolutely. So, we have 0, 0. Here would be at x equals 3, y equals 0. Here would be at x equals 0, y equals 3. So that gives us 7 points to test. Okay, well, let's test. So how do we test? We're going to plug each one of these points into our function. So we start with 1, 1. So we say, okay, 1 plus 2 minus 4. So that turns out to be 1 minus 4 is negative 3. Okay, how about 0, 1? So y is 1, x is 0. 1, 0, minus 2, 0. So 1 minus 2, negative 1. How about 1, 0? So x is 1, y is 0. You get 0, 2, 0, minus 4. So that's 2 minus 4, that's negative 2. How about 4 thirds, 5 thirds? Let's come here. So remember, this is our f on the line y equals 3 minus x. So we can just plug in 3, 4 thirds squared minus 8 times 4 thirds, and then plus 3. Well, that's 9 thirds. So 3, and there's a 3 squared, so that will leave us with a single 3 downstairs, 16 upstairs, minus 32 over 3 plus 9 over 3. 16 plus 9 is 25. 25 subtract 32 is negative 7 over 3. For all of you engineers out there, that's negative 2.3333. Okay, so negative 7 thirds. Negative 2.3333. All right, good. Well, maybe it's good. It's a number. Okay, 0, 0. 0, 0, 0, 0. Yeah, 0. It'd be nice if there were more numbers like 0, but there's not. 0 is unique. It's such a great number. F of 3 comma 0. So everywhere we currently see an x, put a 3. Wherever we see a y, put a 0. So you'll have a 0, 2 times 9, which is 18, 0, 4 times 3, which is 12. So it's going to be 18 minus 12, which is 6. Okay, 0, comma 3. Everywhere there's an x, put a 0. Everywhere there's a y, put a 3. So you're going to have 9 and 0 minus 6, 0. So it's 9 minus 6, also known as 3. All right, so our moment of truth. Here we go. We have our list. And so we start looking at our list. Now, notice what do we need? We need to find the absolute max and absolute min and just the values. We don't need to know the points, just the values. So the absolute max is -3, -1. We're scanning the largest number, 6. Absolute min, okay, scanning the smallest number, -3. And we're done. We found the absolute max and the absolute min. All right. These problems take time. Be patient. Be patient. And, you know, it's not always the length of the problem which is the difficulty of the problem, right? Some problems which take a long time aren't that difficult. They just take time. Don't be intimidated by big problems. Most big problems are just lots of little problems strung together. You can do these problems. You can do these. You're wonderful. You have the capacity. You'll have to practice, don't get me wrong. But with practice and perseverance, you'll be great. All right. Thank you so much for hanging in there. Hope you're having a great week. And maybe, I hope, I get to see you again. Bye.